this video we're going to go over the basics of work, and we're going to derive the three equations to calculate work in different scenarios. So work is defined as the energy transfer to or from an object via the application of force along a displacement. So the units are joules because it's a type of energy. So this is the equation. Work is the integral of force in the direction of displacement. So for this one, find the work of an object with mass m that travels distance p with speed v. So if you write out our equation, the one we were given above, so we know from Newton's second law that force equals mass times acceleration. So if we substitute force in, we get work equals mass. Now with acceleration is also the differential of velocity by time, right? Just like velocity is the differential of displacement by time. So that's the relationship between displacement, velocity and acceleration. So instead of substituting acceleration, we're substituting the differential, and you'll see why later. So now we have this, and don't forget our differential with respect to displacement we had before. So now that we've done that, we can rearrange this part just by swapping dv by dl. So we have work equals mass, then we have dl over dt dv, right? We just swap those because technically they are multiplied together. So, and we established here that displacement, the change in displacement with respect to time, is velocity, and this is what we have here. So we can also rearrange it to get, so if we're going to substitute in velocity, that's what we get. And obviously you get from v2 to v1 whatever v1 and v2 are. So now that we have that, if we do the integral, we have work equals 0.5 mass times v2 squared minus v1 squared. And this might look a bit familiar. It's because it's the change in kinetic energy of the system, which is a form of work. It's probably remembered as half mv squared, which is how we've derived it, but this is another form of the equation. So moving on, find the work of an object with mass m that falls from height h. So this might sound familiar, so it might be ringing bells of like potential energy, which would be correct. So if we write down our equation, so the one we started with, and then we substitute in force equals mass times acceleration, like we did before, because of the second law. So because we're dealing with falling, we've got to take into account gravity, which is gravitational acceleration, which is what we're going to use instead of a. So if we continue, work equals the integral of mass, and instead of a we're going to put g for gravitational acceleration, and of course we have the with respect to displacement like we had before. So now we can integrate. We have work equals, we can take mass and gravity out of the integral because they're not dependent on displacement. So we have between h2 and h1, because it's falling, from a height. And then we have dl. So doing the integral would equal from h2 to h1. So this is the change in potential energy of the system. So this can also be written as cos mg delta h, the change in height. So if we put on the next page, find the work that is needed in order to expand a piston with gas. So if we start out with our original equation, right? So another equation relating force is force equals pressure times area. So we can substitute this in. P and A for pressure and area. Now, something that might ring a bell is you have the area and you have the displacement. So when we're talking about displacement in this case, we're talking about the height, because we're expanding a piston. So when the piston expands, we're going to measure that height, which is the displacement. So the area times the height is actually the volume, right? If you thought of it as like a canister with a piston in, and as that increases, we're measuring the volume, and it goes up. So this is actually the volume. So we can rewrite it as P dV, right? If we take into account those two. So if we assume the pressure is constant, we can take the pressure out of the integral. If not, then we'll have to keep it in. So we're going to assume that it's constant though. So it's not dependent on volume. So we assume pressure is constant. So W equals P from one volume to another, because it's expanding, the volume will change, dV. So once we do that integral, we have work equals P V2 minus V1. And this is only valid when pressure is constant. And that's it.